There are black holes that scare us. And then there are black holes that call our entire understanding of the universe into question. At the heart of a distant galaxy cluster, 5.7 billion light-years away, there exists an object so massive, so energetic, that it refuses to behave the way our best models say it should. This is not just another supermassive black hole. This is Phoenix A, a black hole growing faster than theory allows, sitting inside an environment that should have shut it down long ago, feeding, radiating, and surviving in ways that contradict each other. And that leaves us with an uncomfortable question. Are we looking at an extreme exception, or the moment where our assumptions about black holes begin to break? Phoenix A sits at the center of the Phoenix cluster, a massive galaxy cluster, first discovered in 2010 by astronomers using the South Pole Telescope at NSF's Amundsen-Scott South Pole Station in Antarctica. During a survey of the southern sky for galaxy clusters, the system lies roughly 5.7 billion light-years from Earth. This means the light we observe today left Phoenix A at a time when Earth had only just formed, when its surface dominated by volcanism and impact, its atmosphere nearly devoid of oxygen, and the sun itself significantly dimmer than it is today. At such a distance, not every system can be seen. Only structures that are exceptionally luminous and energetic stand out in observational data. Phoenix A belongs to this category not because it is exotic, but because its physical intensity far exceeds the norm. At the core of the Phoenix cluster lies a massive central galaxy. At its nucleus sits Phoenix A, a supermassive black hole whose mass has been estimated in multiple academic studies at around 100 billion solar masses. Based on galaxy core structure modeling combined with X-ray data from space-based observatories, these values are indirect estimates, but they are widely cited in scientific compilations of the most massive black holes ever inferred. When a black hole reaches this mass regime, the issue is no longer record-keeping. The issue is time. Standard growth models must confront how such an object could form and grow within the finite age of the universe. Phoenix A is not extreme solely because of its mass. Its surrounding environment is what truly distinguishes the system. The Phoenix cluster emits X-rays at extraordinary intensity, placing it among the most X-ray luminous galaxy clusters ever observed. This radiation indicates gas heated to tens of millions of degrees, compressed within the cluster's deep gravitational potential. Matter continuously flows inward, releasing energy on enormous scales. This is not a static system, but one operating at very high intensity. For this reason, the Phoenix cluster has been studied in detail using X-ray observatories, especially the Chandra X-ray Observatory. Its high resolution allows astronomers to directly observe hot gas structures, cooling regions, and interactions between the central black hole and its environment. Chandra data show that the cluster core does not remain stable like most massive clusters. Instead of staying hot, the gas in the core cools rapidly while still being disturbed by powerful energetic processes. This state creates a clear paradox. Under standard models, energy released by the central black hole should heat the surrounding environment strongly enough to suppress rapid cooling. Yet, in the Phoenix cluster, cooling proceeds violently. This paradox is what makes the name Phoenix unexpectedly fitting. The system appears to weaken and regenerate at the same time. When all the evidence is combined, the vast cosmic distance, the extreme black hole mass, the intense X-ray environment, and the simultaneous cooling and activity, Phoenix A is no longer a singular anomaly. It becomes a severe test of our understanding of how the larger systems in the universe evolve. Is Phoenix A truly a single black hole? Or is it the surviving imprint of past mergers between multiple cosmic monsters? Throughout cosmic history, most supermassive black holes do not form in isolation. Most reach their present size through long chains of mergers. As galaxies collide, merge, and their central black holes gradually coalesce. This process is considered a cornerstone of standard galaxy evolution. Each galaxy merger brings not only stars and gas, but also its own central black hole, contributing to the gradual construction of a larger black hole at the core of the resulting system. In this context, the Phoenix cluster stands out as an environment especially favorable to mergers. It is a dense galaxy cluster, where hundreds of galaxies are bound within a shared gravitational potential, moving at high relative velocities, with a far greater likelihood of interaction than in sparse regions. In such an environment, early merger chains could occur frequently. Multiple massive galaxies merging when the universe was still young may have produced an unusually large central nucleus, a massive precursor to what we now observe as Phoenix A. This scenario helps explain why Phoenix A appears to have reached an enormous mass very early in cosmic history. Instead of growing slowly from a small seed, it may have started with a significant advantage, assembled from the merger of multiple already massive black holes. However, even the most aggressive merger scenarios explain only part of the story. Mergers can create an initially massive black hole, but they do not automatically account for why Phoenix A still shows signs of intense growth at the epoch we observe it. After major merger chains conclude, standard models predict that the system should gradually stabilize. Energy feedback from the central black hole is expected to regulate inflowing matter and slow further growth. Phoenix A, however, does not appear to follow this trajectory. This creates a gap in the explanation. If Phoenix A became massive through early mergers, why does it continue to grow rapidly in an environment that should be strongly self-regulating? That gap opens the door to another possibility. Phoenix A may not be a simple black hole in the traditional sense. Its structure, history, or operating mechanisms may differ from the foundational assumptions on which current astrophysics is built. If so, Phoenix A would not merely be a familiar process pushed to extremes. It could signal a limitation within the very models we use to describe the formation and evolution of supermassive black holes. What if Phoenix A does not obey the foundational assumptions of standard astrophysics? Standard astrophysical models are built on a central assumption. Supermassive black holes cannot grow indefinitely. Once they reach a certain threshold, the energy they release feeds back into their surroundings and limits further accretion. This mechanism is commonly known as AGN feedback. As matter falls into the black hole, the released energy in the form of radiation, winds, or jets heats the surrounding gas and prevents it from cooling and continuing to flow inward. In most massive galaxy clusters, this assumption works reasonably well. Hot gas remains near thermal balance. Accretion rates are suppressed, and the central black hole grows slowly over long periods. Phoenix A does not appear to follow this pattern. Observations indicate that the black hole is still accreting matter at a very high rate, far exceeding what standard feedback models would predict. The anomaly is not confined to the black hole itself, but extends to its environment. The hot gas in the core of the Phoenix cluster is cooling at an unusually rapid rate, far faster than in most comparable galaxy clusters. When gas cools rapidly, it loses thermal pressure support. It begins to collapse toward the center, forming continuous inflows that feed the black hole and sustain prolonged accretion phases. In this context, the feedback mechanism expected to self-regulate growth appears to be ineffective. The energy released by Phoenix A is either insufficient to halt the cooling flows, or it is being dissipated in a way that fails to stop accretion. This suggests that one or more foundational assumptions of the standard model may break down under such extreme conditions. Thermal balance, feedback efficiency, or the way energy propagates through the cluster environment may differ substantially from established expectations. Phoenix A, therefore, is not merely an outlier. It becomes the most severe stress test for current AGN feedback models, where even small deviations in assumptions are amplified into clear observational discrepancies. If standard models were fully correct, Phoenix A should have slowed down long ago. The fact that it has not suggests either that we are witnessing a very brief and rare phase, or that something more fundamental is being missed. If the foundational assumptions no longer hold, why has the host galaxy of Phoenix A not been destroyed? By physical intuition, an extremely active central engine should severely damage its surroundings. A rapidly accreting supermassive black hole releases enough energy to expel gas, disrupt star formation, and gradually destabilize its host galaxy. In many other systems, this is exactly what happens. Powerful black hole activity is often associated with heating or clearing out gas, leaving the surrounding galaxy gas poor and gradually shutting down star formation. Phoenix A presents a different picture. Its host galaxy still exists, retains its large-scale structure, and more importantly, continues to form stars at a significant rate. This runs counter to intuitive expectations of an overly energetic core. Instead of a disrupted system, we observe a state of coexistence. The central black hole accretes matter intensely, while the host galaxy has not been quenched. This suggests a delicate balance between absorption and energy release. One possibility is that the energy released by Phoenix A is not distributed uniformly. Jets or radiation may be highly directional, punching through the surrounding environment without depositing enough energy to disrupt the entire galaxy. In such a scenario, much of the cold gas required for star formation could survive in regions not directly impacted. The host galaxy would remain intact, even while its core operates at extreme levels. Another possibility is that we are overestimating the true impact of feedback energy. Models may assume that energy from the black hole couples efficiently to the surrounding gas, while in reality, much of that energy may dissipate without causing large-scale destruction. If that is the case, the survival of the host galaxy becomes less mysterious. The issue would not be that Phoenix A is too powerful, but that we have oversimplified how energy interacts with the galactic environment. In either interpretation, the paradox remains: a black hole showing signs of intense accretion, embedded in a rapidly cooling cluster. Yet its host galaxy has not been destroyed. This forces us to reconsider how we are observing and interpreting Phoenix A in the first place. Are we observing Phoenix A through direct data, or through layers of inference built upon inference? Phoenix A is not an object observed directly in the conventional sense. We do not see its boundary. We do not track stellar orbits around it, and we do not measure its mass through direct dynamical methods. Instead, Phoenix A is inferred through multiple layers of data, from X-ray emission of hot gas, from the structure of the central galaxy, from the cooling rate of the cluster, and from empirical relations derived from much closer systems. Each step in that chain relies on an intermediate model. Models describing how gas emits X-rays. Models linking galaxy structure to black hole mass. And models assuming that relations observed nearby still hold at vast cosmic distances. The issue is not that these models are wrong. Most perform remarkably well within tested regimes. The issue is that Phoenix A exists in an extreme domain, where familiar assumptions may be stretched to their limits. Under such conditions, small deviations in initial assumptions can be greatly amplified in the final outcome. Minor differences in core structure, radiative efficiency, or energy coupling can dramatically alter inferred masses. This does not invalidate the observational data. The X-ray emission is real. The cooling rates are measured. The energetic activity is undeniable. But the way we connect these facts into a coherent picture is inevitably shaped by interpretation. Phoenix A, therefore, is not only a physical object, it is a methodological lesson. It shows how blurred the boundary between measurement and inference becomes when we push observation to the most extreme cosmic scales. In this case, the question is no longer simply how massive Phoenix A is. The question is how we know that, and how much the confidence in that knowledge depends on foundational assumptions. By sitting at the edge of indirect observability, Phoenix A forces science to examine its own tools, not to doubt the data, but to understand the limits of the inferences built upon it. If Phoenix A truly exists as we currently describe it, then it is not merely a rare case. It may be a sign that we are only seeing the tip of a much larger population. If Phoenix A truly exists as we think it does, how many other Phoenix-like systems remain hidden beyond our observational reach? Phoenix A was discovered not because it represents a typical black hole, but because it is exceptionally luminous and highly active. Its intense X-ray emission and powerful accretion made it stand out enough to overcome observational limits across billions of light-years. This ability to detect Phoenix A also reveals a clear bias. We see it because it is extreme. Similar systems that are less active, less luminous, or caught in quieter phases may be entirely absent from current data. This is not unusual in astronomical surveys. Search methods naturally favor the brightest, hottest, and most easily identifiable sources. Objects near detection thresholds, even if physically similar, are easily missed. If Phoenix A represents an extreme state that can exist, there is little reason to believe it is unique. Instead, it may be a rare example that we happen to be able to observe. This suggests that extreme supermassive black holes may be more common than previously assumed. The issue may not be their rarity, but our ability to detect and identify them. Many such systems may exist in less luminous environments, or in evolutionary phases that do not produce strong external signatures. They could still be very massive, yet leave signals too subtle to enter current catalogs. Viewed this way, Phoenix A is not an isolated anomaly. It may be the visible tip of a much larger population of objects that remain unmapped, uncounted, and poorly understood. This raises a broader question for modern astronomy. Not how many extreme objects the universe contains, but how many we are missing because of the limits of our tools and observational strategies. If Phoenix A was detected only because it exceeds ordinary thresholds by a wide margin, then systems that are only slightly less extreme may have vanished entirely from our view. In that case, Phoenix A does not merely raise questions about itself. It raises questions about the entire cosmic picture we believe we are observing. Phoenix A is not the most terrifying black hole ever known. It is not defined by destruction, nor by the apocalyptic imagery often associated with black holes in popular imagination. What makes Phoenix A remarkable is not fear, but the strain it places on our scientific understanding. It is the most stressed black hole we have ever tried to measure, where familiar models are pushed to their limits. Phoenix A does not tell a story of galactic destruction. It tells a story of cosmic phases where self-regulating mechanisms have not yet fully caught up with the processes unfolding within them. It is a story about a universe still learning how to balance itself, about moments when matter, energy, and structure had not yet settled into the stable states we recognize today. Phoenix A reminds us that science advances not only through definitive answers, but through objects that force us to question what we thought we understood. If you want to understand the universe at the edges of what we can measure, subscribe to the channel, because the most important discoveries begin where certainty starts to break.